And we're back at it, nerds. Boop. Like I said, section 3.1, part A, vertex form. There are three forms that we're going to talk about. There's vertex form, intercept form, standard form, and we will talk about them in that order. Tomorrow's notes will be about intercept form, so today is just vertex form. Vertex form is arguably the most important quadratic format, at least for graphing purposes, and that's because it shows you all of your transformations. It might as well be called transformation form, as far as I'm concerned. Here is the general equation. There you go. That's what vertex form looks like. It looks remarkably similar to absolute value. The only difference between vertex form of quadratic and absolute values standard form is instead of absolute value bars, there's a set of parentheses that are squared. The good news about that is that you already know how to find the vertex because it's found the exact same way for quadratics as it is for absolute values. What makes the inside equal 0, comma the number to the far right. And the reason why it's exactly the same? Transformations. Transformations do the same thing to all functions. So our vertex will be h, comma k. What makes the inside equal 0, comma the number to the far right. The vertex of a quadratic is either its bottommost point, its minimum, or its topmost point, its maximum. It's one of those two. Domain for either one of these images means what x's am I allowed to plug in? Well, you can square anything you want. That means you can plug in any x you want. So your domain will be all real numbers. We'll say from negative infinity to positive infinity because interval notation is the way to go. Just like absolute value graphs, quadratics, which parabolas, quadratics are symmetric around a center line. For quadratic graphs, that is called the axis of symmetry. Some textbook authors will just call it the axis. I actually don't know what's in ours because I don't use our book. But there is the axis of symmetry. I'm never going to write axis of symmetry. I might write AOS. I mean, I'll type axis of symmetry on a test maybe, but I won't ever write it in my notes. I just write AOS. And just like absolute value graphs, the axis of symmetry of a quadratic will always pass through its vertex. These axes of symmetry are vertical lines. All vertical lines have a similar style equation. Because a vertical line would only pass through the x-axis, they're always going to be x equals some number. So these axes of symmetry will be x equals, and the number that it equals, well, it goes through the vertex. So it has the same x value as the vertex. Just like that. X equals h. And you do have to say the x equals part. If you don't, you're not getting full credit. There we go. So these four things hold true for all up-down parabolas. I don't think side-to-side parabolas are part of our curriculum anymore. I'll double check on that though. Now you'll notice I've got 4 things here and 4 things here, and it's repeated, but it's for the different object, right? This is an upwards facing parabola, this is a downwards facing parabola, just like absolute value graphs. Positive people smile and negative people frown. So if your A value is positive, your graph opens up. And if your A value is negative, your graph opens down, just like absolute value graphs. So just like absolute value graphs, our range is going to be determined by whether it's up or down, and then the vertex. Because both of these images are bounded somehow. This graph is bounded below by the vertex. This graph is bounded above by the vertex. So when we talk about range, which is the only interval that we use y values for, we're only going to talk about the y values. So when I said bounded by its vertex, what I actually mean is the y value of its vertex. This parabola has a lowest point and then goes up forever. So its range will be from the y value of the vertex, which is k, and go up towards positive infinity on the y-axis. Whereas this one, the y value of its vertex is its highest value. So it's coming up from the negative infinity realm up to the y value of the vertex. And then we have increasing and decreasing. Increasing, decreasing, that's what I used. Remember I described it using a roller coaster. So if the roller coaster is going down, it's decreasing, and the roller coaster is going up, it's increasing as you go from left to right. On this parabola, which side is increasing, left or right? The right side is increasing. And when we say the right side, we're clearly describing a horizontal thing. We use our x's for our increasing, decreasing. So we begin increasing at the vertex, so the x value of a vertex, which is h, and forever to the right. So we decrease on the left side of the vertex. On the x-axis, far left, approaches negative infinity, and it will come from negative infinity all the way up to the x value of the vertex. For the downwards facing graph, it's the exact same two intervals, it's just that they've switched places. Because now the left side is my increasing side. And the right side, whee, that's our decreasing side. So from the vertex and forever to the right, like that. That should be relatively easy. Okay. So what is the parent function? Because the next example, I'm waiting for, I can still see pens moving for this one while I'm talking. Yes?
For the second one, why did you say K instead of H for increasing, decreasing?
Because I made a terrible, terrible mistake. The number of times I said the x value of the vertex and I wrote k like a dingling. Sorry about that. Yeah, the only thing that uses the y values is the range. Darn it. I was doing so good at talking, thinking, and writing all at the same time. At least I thought I was. Making mistakes. So the parent function is y equals, or f of x equals, x squared. This means no transformations. If you had no clue what the parent function looks like, you could just grab a bunch of x values and plug them in. So let's pretend we didn't know what this thing looked like. And we make ourselves a nice little xy table. We're going to plug in 5 values for x, because why not? -2 through +2. And just square those numbers. It's easy enough. Notice the y values in the table are symmetric around this middle point. That's because this middle point is the vertex. Question for me or no? Okay. I don't know why I made my x-axis so big. That was unnecessary. X equals 1, x equals 2, x equals -1, x equals -2, and my y values, I went all the way up to 4. So we just plot our points. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. The axis of symmetry for this one is the y-axis, x equals 0. See, it's the same graph on both sides. You're not going to draw a V-shaped graph. You're going to do your best to draw a U-shaped graph, which is not always the easiest thing in the world to do. It's hard to get curvy. There. Close enough. The point is, you know what it looks like. Transformations are never going anywhere. They're sticking around all year, and we're going to do them again next year in AP Pre-Calc. Transformations are not going anywhere. So I want to know, what are the 3 transformations done on the parent function to get this function? I see 1 on the inside, I see 2 on the outside. Inside changes and outside changes do not affect one another. So my question is, does it matter the order? Well, kind of. It doesn't matter which ones I do first, horizontals or verticals. That's not important. All that is important is I make sure that my horizontal transformations happen in a correct order, and I make sure my vertical transformations happen in a correct order. There's only one horizontal transformation. Horizontal, inside, opposite. I see one thing going on inside my parentheses. It looks like I'm subtracting 4 from my x's. Horizontal, inside, opposite. So I'm not subtracting 4 from my x's. I'm adding 4 to my x's. And what would that do to the graph? What would that do? You guys can shout it out. Yeah. If we add 4 to all of our x values, we just move right on the x-axis. We shift right 4. Vertical, there's 2 of them because I see 2 outside changes. Here's my question. You're all going to shout it out as a class in just a second. It's vertical, outside, same. I see 2 transformations. Do my outside transformations follow PEMDAS or SAD-MEP? Let me hear it. PEMDAS. Outside transformations follow PEMDAS because they do exactly what we think they should do. That means we have to do this multiplication first, multiplying by 1/3. If you multiply something by 1/3, because it's the same on the outside, is that going to make it bigger or smaller? It's smaller, yeah. And that's why we're going to describe this as a vertical shrink. So we have a vertical shrink, factor 1/3. And then that -3 at the end. Vertical outside, same. Looks like you're taking 3 away from your y's. You are. Shift down 3 units. If this was a multiple choice test question and I said, like, hey, graph this equation, you should know that it points up and it has been shifted right 4, down 3. So I have a vertex over here somewhere, thing points up, and this 1/3 is going to make it appear shorter, which actually gives quadratics the look of being fatter. So you'd be looking for a graph that looks fatter than looks. See, I'm saying looks. Looks fatter than the parent function, still points up, but its vertex is down here somewhere. That should be enough to get your questions right if this is a multiple choice graphing question. But it does say to graph it. Here's how we're going to graph our quadratics. The very first thing you're going to do is decide what it looks like. Is it an up or a down parabola? Well, we've already said this one's up. We know it's up because positive people smile. Whee! Okay. And the vertex is going to be what makes the inside equal 0, comma the number to the far right. Or we could just say it should have been 0, 0, and it's been shifted right 4, down 3. So you could read the transformations, right 4, down 3. Sounds like 4, comma -3 to me. That means our axis of symmetry is 4, right? Could someone please tell me why I just missed that test question? Because you didn't put x equals. 4 is not a line. 4 is a number. This is a line. It matters. So let's put our vertex on there. 4, comma -3. That is over here. And I'm going to go ahead and throw that axis of symmetry on there. All right. We need one more coordinate, just one more. If we know one more point on this parabola, then we can reflect that one point across the axis of symmetry and connect our 3 dots with a U-shaped graph. How do we typically find another coordinate? Ilya, what do we normally do? Yeah, we just put in another x, anything other than 4, right? We would just do that. And sometimes that will work for quadratics. Sometimes it's going to cause you an issue, a small, and I'm talking small issue. I don't know about you guys, but I don't like to have to graph decimals. I like to graph pretty points. I want them to hit a perfect grid spot. So if you're like me and you want to make sure that your quadratics are always hitting pretty points, pretty grid spots. I'm going to teach you yes, this is a trick, but it's true because of transformations. All you have to do is look at this denominator. Whatever this denominator is, tells you how far away from your axis of symmetry to go. This is telling me if I go 3 to the left or 3 to the right from my axis of symmetry, I will not have to graph a decimal. That's what that tells me. So that's up to you if you want to write that secret down for yourself or not. It doesn't really matter. If you don't care about plotting decimals, by all means, grab another x. My only other piece of advice would be stay close to the axis of symmetry, because the further you get from the axis of symmetry, the more vertical these things become, and they could just fall off your grid. But since I don't want to plot decimals, I'm going to go 3 away from my axis of symmetry. I'm going to go to the right, because if I go to the right, my number gets bigger. So I'll have a positive in here. So let's go to the right, 1, 2, 3. Okay, 3 to the right puts me at x equals 7. So I want to try x equals 7. So we're going to sub in x equals 7, see what happens. We get f of 7 equals 1/3 Hardest part about this is following the order of operations. What's inside the parentheses first, then exponents, then multiplication, division, then addition, subtraction. 7 minus 4 is 3. Exponents, 3 squared is 9. Instead of saying times, here, we say of. 1/3 of 9, that's 3. And 3 minus 3 is 0. What that tells me is when x equals 7, y equals 0, 7 comma 0 is on my graph. That's right here. I have accidentally found one of the solutions to my quadratic. Whatever, neat coincidence. Since this one is 3 to the right of the axis of symmetry, I can find the exact same dot 3 to the left of the axis of symmetry, and that is enough to draw your U-shaped graph. If you want to, excuse me, if you want to know the y-intercept, you can just sub in x equals 0, and you'll get 16 over 3, which is 5.3 repeating, minus 3 is 2.3 repeating. That's your y-intercept if you want it, 2.3 repeating. But whatever. You have any questions about that? Yes?
What exactly made you pick 7?
So the reason why I chose 7 was because I know through my knowledge of transformations and that if I go 3 away, I'm going to be able to divide by 3. And here's why. When I used x equals 4, this thing's value was 0, right? So what kind of numbers are divisible by 3? Multiples of 3. Well, squaring a multiple of 3 still gets you a multiple of 3, luckily. So I was able to just say, all right, well, if I was 1 away, my difference would be 1. 1 squared is 1. If I was 2 away, 2 squared is 4. I can't divide that by 3. If I'm 3 away, 3 squared is 9. Ah, yes, I can divide that by 3. So it's because this thing was centered around x equals 4. But the squared parentheses value, we want to be a multiple of 3. And the first square that is a multiple of 3 is 9. So I knew that this needed to equal 9. The whole thing. So I needed just the inside's value to be 3.
Sorry, just like a question. Can I make it x equals 13?
Yeah.
Minus 4, that gives you a 9.
Yes, but then you'd have to square the 9. And 9 squared is 81. A third of 81 is 27, and 27 minus 3 is 24. So will it work? Yes. 13 comma 24 is on this parabola. It just won't be on the grid. Yes. But yeah, you could do that definitely if your grid is large enough. You could definitely pull that off. Yes?
Does the trick always work where you just take the denominator of the fraction?
Yeah, the trick always works. Because that denominator of the fraction, even though I'm calling it a trick, it's working because of transformations. And, Mr. M, not every one of them has a fraction on the front. Actually, they do. Because any number that's not written as a fraction will have a denominator of 1. So when there are no fractions, feel free to just go 1 away from the axis of symmetry. I graphed the last one in orange, so I'll graph this one in blue. Go Gators. Our vertex is what number makes the inside equal 0, or you could think of it as transformations. It's supposed to be at 0, 0. It's been shifted left 2, up 7, or you could just say what makes the inside equal 0, comma the numbers to the far right. Whatever makes you more comfortable. Our axis of symmetry, trying to pick a good color. X equals the x value of the vertex, so x equals -2. Like that. And then again, we only need 1 point on one side of this vertical dotted line, and we can just reflect it to the other side and connect our dots. And it doesn't matter what x we choose, as long as we're moving by ones, we won't have to graph any decimals. So we could literally just go 1 to the right. If you move 1 to the right, you're at x equals -1. I could have gone 1 to the left and used -5. It won't make a difference. I'll get the same result. And then again, the hardest part about it then will be just the order of operations. We handle what's inside the parentheses first. -1 plus 2 just gives us a +1. So we have -2 times +1 squared plus 7. That's just -2 plus 7, which is 5. So we have the coordinates -1 comma 5 on this parabola. -1, 5 is here. That coordinate is 1 unit to the right of the axis of symmetry. That means there's a matching one, 1 unit to the left of the axis of symmetry. If you want to have a very accurate graph, you could find more y values, x comma y's if you want. Like if you wanted to know what the y-intercept is, you could just plug in x equals 0, right? By the way, that's true for any polynomial, any function. You want to know where it crosses the y-axis, you just use x equals 0. That's true for all graphs. Anyway, if I throw a 0 here, I get a 2 squared, which is 4. So -2 is -8. -8 plus 7 is -1. So it crosses way down there, and its reflection is right there. Look how steep that graph is. That's tough. Let's see. Good enough. So if you have the ability to turn an equation into a graph, you should have the ability to turn a graph back into an equation. Same thing we did with our absolute value graphs. Exact same thing we did. Questions on the graphing process before we move on to finding the equations? Everybody's really comfortable with this because they remember from Algebra 1? Is that what's happening? Maybe. Okay. What should I look for first? Vertex. It's hanging out right here at -3 comma 4. Let me tell you what we know so far. We know the equation is f of x, or y, equals unknown if it has an a value or not. There's going to be a set of parentheses like this. The -3 for the vertex is because the thing's been shifted left 3. So I'm going to see a +3 plus 3 in here. And then it's been shifted up 4, and that's why I'm going to see a +4 out here. we have almost the entire equation. Barry.
Do you need the axis of symmetry?
I don't need to write the axis of symmetry, but we can, because it's going to be x equals -3. It's not wrong. It's absolutely right to have it on there. It's just not necessary. But what am I going to do? How am I going to figure out what this a value is here? Well, what do we know about it, first of all? It's negative. How'd you know that, Thomas?
Because the parallel is pointing downward.
Yeah, because it points down. So because this thing points down, we know it's negative. Please do yourself a favor. Don't put a negative sign in front of it. Let the math give you the negative answer, which makes you happy because it confirms to you that you already knew what you were talking about. But what are we going to do? How could we possibly figure out this variable? It'd be nice if more than 1 or 2 people spoke to me today. I know, Thomas, I know. I should just find a random victim. Ryan, thank you for volunteering. You just saved that back table back there that's all smirking from having a 1 in 4 chance of being a victim. Because I was going to pick one of the 4 of them.
How many times it moves over?
What do you mean? When you say it moves over, what are you talking about?
You can find the
Denominator.
denominator.
Okay, can you... What do you mean by that?
But you know the trick?
The trick, which told me what?
How far away, how far you move?
How far I moved to find what?
I think I know what you mean.
I know what he means too. I'm trying to get him to say the words.
If the nearest like whole point is
Oh, we're
over
looking for a...
the bottom has to be 3.
We're looking for a pretty point. Ryan, we're looking for a pretty point. You had the logic backwards. Instead of trying to count to the next pretty point, use the next pretty point to tell you what A is. And the closest one that I can see is happening here. Or its reflection right there. So I'm going to use 0, -2 to find A. Because 0 is an x value, and -2 is a y value, I can substitute that x and that y in. So we say -2 is A that we're going to find, 0, then we got that +3 still, and this +4. A is now the only letter we have in the equation. We can easily get it by itself. 0 + 3 is 3, and 3 squared is 9. Just get A by itself. Subtract 4. I'm out of vertical space, so I'm going to scoot up here. -6 is 9A, and divide both sides by 9. You're going to need to reduce your fraction. So A is, look, it's negative, just like we said it would be. And 6/9 reduces to 2/3. The equation of our parabola in vertex form is y, or f of x, equals -2/3 on the front, x plus 3 quantity squared plus 4. There it is. Identify your vertex, put it into the vertex form as your h and your k, find one more pretty point, use that as x, y. That's how you identify what your a value is. Pretty cool, huh? All right. That's if you have a picture. So how would this example be any different? It's not. Thank you. Daniel says it's not. He's right. It's exactly the same question. I mean, the vertex is different. This is a coincidence that this is the y-intercept. This is coincidence, 100% coincidence. I don't want anybody to think that we're always going to use the coordinate 0, -2 or anything stupid like that. It just happened. But this is legitimately the exact same kind of question. The only difference was handed the vertex rather than looking at the vertex. So since it's the same style question, I'm just going to write same as above. Draw an arrow. and I'm going to move on with my life. Because it's not any different. And remember, I said you could use any pretty point, not just the y-intercept. Right? Okay. What I really want to talk about, though, is the last question. This is not vertex form. I don't know if you noticed, but all of your vertex forms inside the parentheses say x plus or minus a number, don't they? None of them had your x negative. None of them had a number in front of your x. So this is not vertex form. And this is much more difficult to graph than vertex form is. I want it in vertex form. So we're going to manipulate the numbers a little bit. We're going to play with it. Hopefully that made it onto the mic. I did that pretty close to the microphone. Cracked my fingers. Here's how. The part that's stopping it from being vertex form right now is inside the parentheses, right? It's a problem for us, isn't it? Yes, it's a problem. So you know what you're going to do? Go make me say an F word. You're going to factor it. Yeah, I know. Big scary F word. We're going to factor. Because we need the inside of these parentheses to say x plus or minus a number. So we need this negative 1/3 to come off of the front of this x. So we'll simply divide out, factor out a negative 1/3 from both terms. If you divide this by negative 1/3, all that's left is positive x. This number is positive. If you divide it by a negative, you get a negative. But how many, let's see, you could think of this more than one way. You could either think to yourself, how many 1/3 fit into this one? Or you could ask yourself, what does dividing by 1/3 actually mean? It's whatever you want to do. But when you divide by a fraction, that's that whole keep, change, flip garbage. When you divide by a fraction, you actually multiply by the reciprocal. So instead of saying divide by 1/3, say times 3. 1 divided by 1/3 is the same thing as saying 1 times 3. Or again, you could say, how many thirds do I need to get a 1 whole? You need 3/3. Did you not understand? You're whispering over there. Okay. I'm just making sure. All right, so here's what this tells me. I'm going to have to keep writing the minus 12 and the plus 5, but take this trip with me. So we've got this negative 12. I'm going to write a set of brackets. Because inside those brackets, I'm going to write this. We're closer to vertex form, but we're still not there yet. These two objects are multiplied to each other. In Algebra 1, you should have learned that when you have multiple objects inside a set of parentheses that are being multiplied together, and those parentheses have an exponent, the exponent will actually be applied to all of the stuff on the inside. In this, I have the negative 1/3, and in here, I have the x minus 3. Negative 1/3 times negative 1/3, positive 1/9. Literally square the 1 and square the 3. So negative 12 times 1/9, and then I have x minus 3 squared plus 5. Look how close we are to vertex form. Negative 12 times 1/9 is just negative 12/9. And then we'd reduce the fraction, and we're finished. 3 goes into both of these, so it's negative 4/3 x minus 3 quantity squared plus 5. That is vertex form. And you could have done the exact same style of mathematics when we were working with the absolute value stuff. Nerds, stupid phone.